Okay, so first, let me just announce in person. I made an announcement on Canvas saying that unfortunately I have to cancel my office hours this evening. I know that must be very disappointing. But I will hold office hours tomorrow, 11:50 to 1:20 p.m. to make up for that. Sorry about that. If you can't make that, email me and we can find some time to meet tomorrow to address any questions you have. Okay, so I'll just write this out. No office hours at night. Make up office hours. 11:50 to 1:20 tomorrow, Thursday. Five 40A, Nightingale. Or email me. You can't make that and you want to talk. Okay, so on Monday, we left in the midst of an example where we had to recall how to do polynomial division, right? So we were attempting to calculate the following integral, x to the fourth plus x cubed plus x squared plus 1 divided by x squared plus x minus 2 dx. And we successfully completed a polynomial division. Our goal here is to eventually try to use partial fractions, but we know that that only works when the degree of the denominator is greater than or equal to the degree of the numerator. So as it stands, we can't apply partial fractions, right? So our remedy to this situation is to use polynomial division to re-express this rational function as a polynomial plus a rational function that we can use partial fractions on. So let me remind you of the calculation that we made on the end of Monday. So we had our written in our standard division notation, right? X to the fourth, x cubed, x squared, plus 0 times x plus 1, right? I'm not going to redo the calculation, but what we concluded was that the quotient is x squared plus 3, and the remainder we found to be negative 3x plus 7. Now, what this means is that we can rewrite our integrand in the following way. The integral of x squared plus 3 minus, or really, I guess I should just say plus, negative 3x plus 7 divided by the original denominator, x squared plus x minus 2 dx, right? This is the part of this polynomial that the divisor divides evenly, right? And with our remainder, we can't do anything with that, right? We can't divide this by this because the denominator has greater degree than the numerator, so we can't divide them. But now we're in a situation where we can apply a partial fraction. Yeah. Okay. So that is to say, now we will use first linearity, right? We'll take the integral of x squared plus 3 dx plus integral of negative 3x plus 7 divided by x squared plus x minus 2 dx. Okay. So now we can use partial fractions. What is the first step to do so? What should we do?
Factor the denominator.
We should do our best at factoring the denominator. Yeah. So fractions. So we first factor the denominator. How does this denominator factor? Any flex their algebra skills here? Yeah, x plus 2 and x minus. Yeah, x plus 2 and x minus 1. Good. Okay. So what we have is we're looking for constants. A divided by x plus 2 plus b divided by x minus 1 equal to negative 3x plus 7 divided by x plus 2 times x minus 1. Okay, which in turn gives us the following equation. When we clear denominators, a times x minus 1 plus b times x plus 2 equals negative 3x plus 7. Okay, what's our next step? Yeah.
You substitute in different values of x until one of those equals 0.
Yeah, exactly. We one by one find the values of a and b by inserting a value of x that turns one of these summands into 0. So let's just start by looking at what happens when x equals 1 and this first term goes to 0. Okay, so at x equals 1, you get a times 1 minus 1 plus b times 1 plus 2 is equal to negative 3 times 1 plus 7. What do we get when we do some arithmetic here? This implies that b is equal to 4/3, right? Okay, and then we'll go back to our original equation and see what happens at x equals negative 2, which will send this second term to 0, right? So we get a times negative 2 minus 1 plus b times negative 2 plus 2 equal to negative 3 times negative 2 plus 7. Again, just do some arithmetic here to conclude that a is equal to negative 1. All right. So our original integral is equal to, then let's not forget our polynomial part. Right? We have x squared plus 3 dx plus the integral of negative 1 divided by x plus 2 dx plus the integral of 4/3 divided by x minus 1 dx. Okay, so now we finally arrived at a point where we know each of our integrands how to find the antiderivative. Yeah.
Is A equal 5?
Okay, let's see here. We have 6 plus 7 is 13 divided by -3. How did I get -1? Yeah, I'm sorry. You know what I did in my notes is I dropped a negative sign here. Good, thank you. I'm really bad at calculation, just to let you know. So always check what I say. Gonna be wrong a lot of the time. Okay, so this is wrong. Instead, what do we get here? What did I just say? This is 6 plus 7 is 13. Yeah, so we get -13/3. A is equal to -13/3. Good, thank you for keeping me honest. But we still know how to deal with this integrand, right? Despite my calculations being slightly incorrect. So first of all, what's the antiderivative here?
Or which one?
For the first term.
It'd be 1/3 x cubed plus 3x. Yeah, 30x.
We'll have a single constant at the end. I'll just save that
Right,
till the very end. Okay. So minus, we'll take our constant out front. 13/3. What's the antiderivative of 1 over x plus 2?
Not the one of the absolute value of the constant.
Yep, good. Plus, we'll again take our constant out front. And what's the antiderivative of 1 over x minus 1? Much similar to this, right? It's just the ln of the absolute value of x minus 1. Plus c. So, again, a lot of the integration of arbitrary rational functions boils down to remembering everything from algebra 2. Okay, let's see a much more involved example of what might happen. So let's try to compute the antiderivative of x plus 1 divided by x minus 5 times x squared plus 6x plus 11 dx. Okay, so right off the bat, this is a function that we don't know how to find the antiderivative of just from the list of functions that we know, right? So what we notice, what's the degree of the denominator? Is 3, yeah. And the degree of the numerator is 1. So we should be able to apply partial fractions, right? Okay. Well, how do we factor this? Not so easy to factor this, but let's see. I want to guide us through a process that will remind us yet again of another tactic from algebra that might come in handy. Okay. In an attempt to factor the quadratic term, let's complete the square. something that you remember? Completing square. Okay, so what we're going to do is, let me remind you of what this process is all about. Observe that in general, x plus a squared is equal to x squared plus 2ax. Yeah, ax plus a squared. So that is to say, whenever we have a quadratic that is the result of squaring a binomial, our linear term has a coefficient that is even or divisible by 2. So what we want to do is take this quadratic term and turn it into a square plus some other constant. Okay, so to make x squared plus 6 plus 11 a square, and really I should put make in parentheses, right? Because it's not actually going to be a square, it's a square plus some constant. What we'll do is divide the coefficient of x by 2. Square the result then add and subtract it. To the polynomial. Right? That is to say, since a square has this form, if I take the linear coefficient, divide it by 2 and square it, that's what the constant term should be if it were a square. Right? So I'll take 6 and divide it by 2 to get 3, and then square that to get 9. Okay, so this implies altogether that x squared plus 6x plus the plus or minus plus 11 is equal to x squared plus 6x plus 9 minus 9 plus 11. And I've added 0 in a clever way here, so that this is a square, right? Okay. So what this gives us is x plus 3 squared plus 2. Okay. So now, what does this tell us about our original polynomial, x squared plus 6x plus 11? Think about what information this is giving us relative to the task of trying to factor our original polynomial. Any thoughts? Well, let me make a couple comments. So when we factor a polynomial, the constant terms of the factors are the roots, right? So that is to say, if we were able to factor this polynomial, it'll have two real roots, right? So if we set this equal to 0 and try to solve, what happens? Yeah,
You get square root of -2.
right. The fact that this implies that we have a square number equal to a negative number means that this has no real roots. So x squared plus 6x plus 11 has no real roots. Therefore, it's what we call irreducible. Right? That is to say, we can't factor it. It's already in its lowest terms. Okay, so this is a bit different than the examples that we've seen involving partial fractions, right? Because we have an irreducible quadratic term in the denominator. So what do we do? Well, there's no reason you should know this. I'll just tell you. Okay. Partial fractions. Now takes on the following form. We have our original expression, x minus 5 times x squared plus 6x plus 11 will now be equal to a over our linear term, x minus 5, plus bx plus c divided by our irreducible quadratic term. Okay, so note. Numerators in partial fractions are always 1 degree lower than denominators. Okay, so when we're able to resolve the denominator into all linear factors, we always have constants, right? Because linear things are degree 1 and constants are degree 0. But now, since we have an irreducible quadratic term, we have to have a linear term in the numerator with unknown coefficients. Okay. And this applies in general. If you come up with a irreducible 4th degree polynomial. Why did I skip irreducible 3rd degree polynomials? Anybody remember this from algebra? Yeah, there are no irreducible cubic polynomials, right? You'll always have at least one real root. You can either factor it into 3 real roots or an irreducible quadratic and a real root. So that's why I didn't say anything about cubic. But in general, you may come up with a higher degree irreducible polynomial. We won't do that to you, but this is just the general landscape of things. Okay. All right. So let's now proceed as we would usually. Let's clear denominators.
Why should put an X in the numerator with B?
Because of this remark, that the numerator has to be a degree less than whatever the irreducible factor in the denominator is.
Why not proceed to the?
Well, yeah, so this is a general linear polynomial, right? A linear polynomial has bx plus c, right? You have a coefficient on x and a constant term. That's the generic linear thing. So that's just what we put in the numerator of an irreducible quadratic term.
That's always just one less thing. I think, too.
That's right, yeah. If it were 2 less, then this would just be a single constant. If the degree were 2 less. I'm sorry,
If it was just X, it would just be
if what were just x?
if the no.
Oh, yeah, if the denominator was a linear term, then yeah, we would just have a constant. Yeah, exactly. Okay, good. So let's clear denominators. Your denominators. What does this give us? X plus 1 equal to a times x squared plus 6x plus 11 plus bx plus c times x minus 5. Okay. So let's do the easy thing first. Let's see what happens at x equals 5. We'll cancel the linear unknown factor. At x equals 5, what do we get? We get a times 5 squared plus 6 times 5 plus 11 is equal to plus b times 5 plus c times 5 minus 5 is equal to 5 plus 1. Okay, so all together, what do we get here? We get 6, 5 plus 1 is equal to, I believe this is 66a. What would that be? Right, everybody agree with that computation? Okay, good. So a is equal to 111. Okay. So here's how do we address B and C? Right. Ostensibly, we should pick something that sends this to 0, but we just convinced ourselves that there is no real number that makes this polynomial 0. So what do we do instead? Yeah. Well, it turns out that actually doesn't help very much. At least not immediately. We eventually will do that, but not before some manipulations. What we'll do is multiply this out, and this a will be distributed through this polynomial. Then we'll get some polynomial which has coefficients in terms of a, b, and c. And then what we'll do is derive some new relationships between the coefficients on that come from this and the coefficients of this polynomial which it must equal. Yeah. that's not clear from what I said. Maybe working it out will make it clear. Okay? So for B and C, we expand and compare coefficients. Okay, so in other words, what do I get? I get ax squared plus 6ax plus 11a plus b x squared minus 5 b x plus cx minus 5c. Just cleaning this up a bit, combining like terms. What do I get? I get a plus b x squared, right? Combining the x squared terms. Plus 6a minus 5b plus c x, yeah, plus the constant terms 11a minus 5c. Okay. What do I mean by compare coefficients? What I mean is that we have to remind ourselves that this whole mess of a, b, and c coefficients is equal to the polynomial x plus 1. Yeah.
Is this supposed to be a B where that 5 is?
Oh, yeah. Good. Thank you. Sorry. Good. Right. So, what does this tell us? What is the coefficient on x squared in this polynomial? Zero. Yeah. Good. So that implies that if this is an equality of polynomials, a plus b has to be equal to 0. Okay. Let's just write down all the relationships before we do any solving. So what's the coefficient on x in this polynomial? 1. So that means 6a minus 5b plus c is equal to 1. And the constant term is also 1, so that means 11a minus 5c also equal to 1. Okay. So first of all, we determined what a is, right? A is 111. So this equality implies that b is equal to negative 111, right? And in fact, this is superfluous information, right? We can just jump right down to here. We know what a is, and this involves only a and c. So if a is 111, we got 1 here, minus 5c is equal to 1. C must be equal to 0. Okay. So altogether, what do we have? Altogether, this means that our original rational function is equal to the following. 111 times 1 over x minus 5 minus x divided by x squared plus 6x plus 11. Okay, so don't forget that we are ultimately trying to integrate the rational function on the left. It's taken us quite far afield. However, let's continue. There's still more manipulation to do before we can actually get this in an integrable format. I'm sad to say. Well, it's horrific, but also fascinating, right? That you might have to do this much work. But the point is that these are all basic algebra techniques, things that were known before the advent of calculus, that we can use to manipulate functions to get them in an integrable format. You had a question first.
Yeah, I was just wondering exactly how you got from the variables to that expression below.
Ah, right. So both A is 111 and B is negative 111, right? So I have a 111th here and a negative 111x here, right? So I left the negative inside and pulled the 111th out.
Okay. Oh, right, and you just plugged it back into that.
Right, right. I plugged my A, B, and C back into this expression and then pulled the 111th out.
We're not gonna have questions long our quiz.
No, no, you only have 20 minutes to do the quiz. This is more. What?
20 minutes?
Yep,
So how long are these quizzes gonna be?
20
Like,
minutes.
how many questions?
Don't worry, it'll be appropriately timed.
Take your word for it.
Yes, I think that's what you have to do. So, right, we still have more work to do to make this integrable. Yeah. What is it that we'll do? In order to make this integrable, more algebra. Okay, so namely, we just want to focus on rearranging this last component here, right? That is to say, x divided by x squared plus 6x plus 11 is equal to, well, now let's use again our completed square format of the denominator. And soon you'll see why we choose to do that. And I'll also add 0 in a clever way to the numerator. Okay. This might seem, yes.
Like, do you have to add x or +1 to the x when the 1 over 11 distributes? You still have the c, or is that the c?
Well, remember the c we determined to be 0.
Oh, right. So
Right, yeah, it became 0 here. Good. Okay. So this is what we'll do. Okay, so what we have all together. Now, this step might seem somewhat mystifying, but now let's go all the way back and take stock of where our integral sits now. Okay. Look again at the integral. Let's combine all the information that we have. So the thing we originally wanted to evaluate, squared plus 6x plus 11, we can now say is equal to the integral of 1 over x minus 5 dx. Remember, just our, oh, I'm sorry, I forgot my 11, my 111 up front. That's what was confusing me in my notes. Okay, so we have 1/11 out front times the integral of 1 over x minus 5 dx minus the integral of x plus 3 divided by x plus 3 squared plus 2 dx plus 3 times the integral of 1 divided by x plus 3 squared plus 2 dx. Okay, so we're in kind of good shape here. We know how to evaluate this, right? This is something that we're getting very used to. 1 over a linear polynomial has antiderivative ln of the absolute value of the linear thing, right? How about this second summand? How might we address that?
Kind of taking a shot in the dark here, but would you cancel out the top and the bottom x plus 3? So it would be 1 over x plus 3 plus 2.
So
You can't do that sum of.
yeah, exactly. You can't split up a denominator like that. Yeah, maybe a U substitution will work here. What should we choose for U?
X plus 3.
Well, if we take the derivative of x plus 3, what do we get? 1, right? So in other words, if we choose that for our U, we still have a function that we didn't get rid of, right? So maybe remember the rule of thumb for a U substitution. Try to include as much as you can into the U. Maybe the whole denominator will work. Let's try it and find out. Okay, so part by part. Let's first work on this part that we were just discussing. We're pretty confident about this. We'll come back to that at the end. Let's start in the middle here. Right, so negative integral 3 divided by plus 3 squared plus 2 dx. The suggestion was to let U be equal to x plus 3 squared plus 2. Then we get du is equal to, what's the derivative here?
2x.
It's 2 x plus 3, right? And that's it, yeah. Dx. Okay, so we get a constant factor of 2 that we have to flip on out to the other side, right? Okay, so what this gives us is negative 1/2 the integral of 1 over u du, or something that we've hopefully become very familiar with by this point, negative 1/2 ln of the absolute value of u. And since I would like to have my final answer in terms of x's, I will put the u back in, ln of the absolute value of x plus 3 squared plus 2. Let's see. Of course, when we put all these together again, we're only going to have a single c as per usual. Okay, now let's take a look at this last summand. 3 times the integral of 1 divided by x plus 3 squared plus 2 dx. How do we cope with this?
Yeah, I'm sorry, I'm confused where the negative 1/2 comes from.
Okay, so the negative sign is just from this negative sign.
Yeah, the 1/2.
And the 2 comes from here, right? We have,
Oh, you're pulling out.
yeah, what we're trying to get rid of is x plus 3 dx, and we get a 2 x plus 3 dx. So we move this 2 to the other side, and it becomes part 1/2 du.
Yeah.
Okay, good. So how do we address this part of the integrand?
Use substitution.
Yeah, maybe we should try use substitution again. What should we use as u this time? X plus 3, an interesting suggestion. Let's give it a try and see what happens. So we let u equal x plus 3, then du is equal to dx, right? The derivative of x plus 3 is just 1. Okay. So we are left with 3 times the integral of 1 divided by u squared plus 2 dx. Does this look familiar? I was going to say no, but I see some hands. Yeah, go ahead. So close. We didn't discuss arc cotangent. Yeah. So it's one of the arctan antiderivatives. Remember, we very briefly discussed a slightly more general formula for the antiderivative of something that results in an arctan where we had a constant squared added. Right? Remember this slight modification? Like try to verify this yourselves by using u substitution in the appropriate way. That was a couple days ago, right? So in order to recognize that, let's slightly rewrite this. Now, oh, I'm sorry. Yeah, they're not keeping me honest. This is exactly the formula for an arbitrary constant A that we wrote down for arctan, right? Okay, so that is to say, what do we get here? We get 3 divided by A, this number squared, root 2, times inverse tangent of u divided by A, the number that we were squaring, plus C. Of course, as I just said, for our last component, we want our answer to be in terms of x. So I'll substitute u back in. Equal to 3 divided by root 2 inverse tangent of x plus 3 divided by root 2 plus c. Now, before we go on, I just want to point out that this contradicts the rule that I just told you in the last step, right? That you, in general, should try to include as much into u as possible. Here, if we had expanded what we called u, if we had included the square or the square plus 2, first of all, we wouldn't have gotten what we need to substitute du in for dx, right? We need a derivative of just one. So the real rule is that you have to pay attention to what you're looking to take out with the differential dx. Okay. Okay, so finally, just for completeness, I'll write this down. Confident that everybody knows this already. It does actually depend on a slight u substitution. Okay, so all together, what do we get? The integral of x plus 1 divided by x minus 5 times x squared plus 6x plus 11 dx is equal to 1/11 times the ln of the absolute value of x minus 5 minus, did I write this? Minus 1/2 ln of the absolute value of, well, I can just now write this in the standard format, right? Remember, this is just the completed square version of our original irreducible quadratic factor of the denominator. Plus 3 divided by √2 inverse tangent of x plus 3 divided by √2 plus c. That was a lot, right? Took us almost an entire class period to do this, and we started last time. So rest assured, you won't see anything like this on a quiz or a test. The point of this example, again, is just to kind of illustrate all the things that, all the nuances that you will become accustomed to making choices about as you progress in the course, okay? This is a mega example that includes pretty much all the algebra that you'll need to remember and employ on a semi-regular basis. Maybe not all at once like this, but in some form or another, pieces of this will be required at various places.
Another question where you did the inverse tangent.
Mhm.
I just want to understand, like, when you turn the 2 into square root of 2, like, how you get to the result that it is inverse tangent of u over square root of 2.
Right, so this goes back to a theorem that we discussed, let's see, I think it was Monday. And if not, then it was Thursday. Right, it was something I asked you to verify. Yes, here we go. Where am I on the board here? Good, I'm right here. So this is something that might come up. This is something that you should have on hand when you're doing homework and try to remember when you're taking a test or quiz. Recall the antiderivative of 1 over x squared plus a squared dx is equal to 1 over a inverse tangent x divided by a plus c. Okay, we didn't actually derive this, but if you take for granted the formula for the case where a is equal to 1, you can derive this by using a substitution with u equal to x divided by a, which requires you to do some algebra to get that form here. Okay, that's what I asked you to do at home. You don't have to, but it's valuable to remember this formula. So now you see, at this point, it takes a bit of insight to just be like, oh, well, 2 isn't a square, but I can just take the square root and then square that to get 2. So my a is square root of 2. It's kind of a finagling of the numbers.
Why can't the C at the end be inside of the bracket?
It absolutely can.
It can be.
Yeah, I just, if it's inside the brackets, then I divide C by 11 and it's still a constant.
Right.
So I could put it in the brackets if I want.
Oh,
That's an acceptable answer on a quiz. More a matter of taste than anything. Right. So, good. Here's what I want you to do, sometime over the next couple days. It's not important for the quiz, I'll tell you that right now. But I would really like you to do this, sometime. So I want you to read example 1.3.5 in the textbook, which starts at the bottom of page 47 of textbook. And it deals with partial fractions for repeated linear roots in the denominator. Here's what I mean. So, for example, if you were given the following rational function, 1 divided by x plus 2 times x minus 1 cubed times x squared plus 4. Well, so based on our discussion today, for the single linear root of the denominator, we just have a constant in the numerator, right? And then it's not too hard to convince yourself that this is an irreducible quadratic, right? There's no real solutions to this. So we know that we get a linear numerator for this term, x squared plus 4. What do we get for this 3-time repeated linear factor of the denominator? Well, please read this to find out. Okay. I just want to make good on some comment I made that you can apply partial fractions to any rational function with the right restrictions. That is, as long as the denominator has degree greater or equal to the numerator, then there's just some rules about the different types of irreducible things you can get when you factor the denominator. And this won't be all that important to us, but I would really like you to know about it.
Isn't entirely related. Where do we find homework
It's all on the syllabus.
on the syllabus?
Yeah, so
Is
at
there
the,
like links to files?
no, it's just in the textbook.
Oh, right. Okay.
Right, it's just a
Like
list
page
of,
numbers.
yeah, it's just a list of, so at the end of every section, there's a collection of exercises. And on the schedule that's included in the syllabus, there's just a list of problems from each section that if you are comfortable with those, then you've mastered the material from that section. Okay. Good. All right, so we have 5 minutes left. I'm going to tell you just an introduction of what our next topic is. And then So for the quiz, we'll only cover up to what I just said now, integration with partial fractions. We won't have anything about improper integrals, which is our next topic. So, right. Right, so, call the fundamental theorem of calculus. If capital F is an antiderivative of little f, then we have the following. The definite integral of little f of x dx from a to b is the antiderivative evaluated at b minus the antiderivative evaluated at a. Right? It's hopefully familiar. I haven't talked about definite integrals yet, but I think there is a concerted effort to have some discussion about this in calculus 1 at the end of the course, right? Okay. So, but what if f has an asymptote at x equals b? Or what if we want to try to integrate over an unbounded region, unbounded interval? Like, for example, negative infinity up to b. Well, the standard definition of an integral doesn't allow for either of these situations. But what we can do is take a limit of a series of integrals for which f is defined. Say, for example, in the case of an asymptote at b, we can take the limit of each of the integrals of the sequence of integrals, moving the constant closer and closer and closer to b, and see if we can make sense of whether that limit is finite or not. And we'll define this to be the value of the integral if it does in fact converge. Right? This is the meaning of the term improper integral. It's not integrable by the definition of integrability, but we can make sense of some limiting process that gives us a finite value. This is what we'll be discussing tomorrow and the next few sessions. Okay, so have a good evening. Sorry again about the office hours. Just let me know if you'd like to meet other than the time that I scheduled tomorrow. Okay. Yeah.
I noticed that we're not gonna have anything like this on the food there, to this extent.
Yeah.
This is like the best practice there, right? Like.
Yeah, right. The problems that make you do the most usually are the best type of thing that can cement things in your head.
Okay. Yeah, so I'm gonna work on these.
Okay.
Thank you. Remember, what comes with the quiz is everything in the homework that things, that's like everything before the first quiz, like every topic.
No, it's only what we covered, so we might be a little behind. The schedule on the syllabus. It's just what we did in class.
So, yeah, I think, yeah, I read that, also in the homework, that incorporate integrals before the quiz, and that doesn't count.
That's right, the quiz that has no improper in it.
Okay.
So normally a identity for n-1 is 1/x squared plus 1, right?
Yeah, if there's no A up here.
Okay, and that's the only difference for that, for this one, and I guess it's just identity.
Yeah, it's helpful.
I'm sure I could try it.
Yeah, it won't come up that often, but it's helpful here.
Okay, and then the only difference is this term is squared, but then you pull out, so then you pull it out. So it's like a
Did you start the, did you finish the?
Yeah, well, I think the way to think of it is when you have a +1, the 1 is.
Right,
Yeah.
right.
Okay, or not to be the same, but.
Yeah.
Okay, then last week, I need to remember 1/a in front of it. So
Like
you
I
pull
started
out-
with.
That's a good way to, if you remember the regular content.
I gotta
Yeah,
finish
that's-
that.
yeah.
Yeah, I don't.
Look,
Is
yeah,
that-
I might just go to the library. right now.
No,
Yep.
the first homework, because it said in the homework that the first week, it wasn't like flat.
Like new stuff.
Yeah, it wasn't new stuff. The new stuff starts. But it's all the group of practice.
Thank you.
Thank you.
Right.
Have a good evening.